Hi everyone, welcome to the Earth Science Reasons Review podcast series created by the Hommocks Middle School Earth Science Department. Today we're going to be talking about Kepler's first law, and specifically ellipses, and we're going to touch base at the very end about Kepler's third law as well. So what's an ellipse? It's a question you're probably asking yourself. It's a rounded shape, and a lot of times those rounded shapes are going to vary in the roundness or the flatness of those shapes. So you can see here that you're going to go basically from a perfect circle to a completely flat line and a bunch of shapes in between. Okay, so that's essentially what an ellipse is going to be. Now we're going to talk about a little bit later in terms of how round or how flat some of these shapes can be and how we can determine that mathematically. Okay, well, it basically comes down to Johannes Kepler, his first law, which basically states that all the planets that revolve around the sun, they're going to make a trip, they're going to make an orbit around the sun, are going to take a somewhat of a elongated path around the sun, not a perfect circle. Much like what you see in this animation here. Okay, all of those orbits by Mercury, Venus, Earth, and Mars, okay, are somewhat oval shaped. They're not going to be perfect circles. You can see here as well, you can see that the Earth is traveling around the sun. Notice that the sun's not directly in the center of Earth's orbit. It's kind of moved in this perspective to the right hand side of the orbit. You notice that it's not a perfect circle, it's what we call an ellipse. So we determine how round or how flat an orbit is based upon eccentricity. So that's basically, it's a measure of how round or how flat, or you could basically say how oval an ellipse is going to be. Now mathematically, when you do this, your eccentricity is going to be somewhere between 0 and 1. You're always going to go to 3 decimal places after the decimal. If you have an eccentricity greater than 1, you divided incorrectly. Okay, and there's not going to be any units. Your units automatically cancel out. Okay, so a perfect circle is going to have an eccentricity of 0. Okay, completely straight line is going to have an eccentricity of 1. Alright, so on page 1 in your reference table, you have your formula. Distance between the foci divided by the length of the major axis. Okay, so you can see you're right here. That's where your equation is going to be, right on the front page of your reference table. That should be familiar because we've already dealt with the density. So here's what we're going to do. Your sun is always going to be one of your focal points. Okay, the second focal point is going to be some spot within that orbit. So what you're going to do is you're going to measure the distance between those two dots. Then you're going to divide that by the length of the major axis, which is going to be the line, the imaginary line, A and B, that's going to go through the widest part of the ellipse through those points. So that is going to be your major axis. So here's a quick example. Okay, and I had already stated that the sun's one of your focal points. So XY is 2 million miles. Distance between A and B is 10 million miles. So XY are your two focal points. That's your distance between the foci, divided by the length of the major axis. Major axis is A to B. So your 2 million miles divided by 10 million miles will turn out to be an eccentricity of 0.200. Notice go to 3 decimal places after the decimal point, the thousandths place, and there's no units. Now, coming back again to your page 15 in the reference table, your solar system data, you can see that there is a column for eccentricity of orbits. You see that for the most part, all of your orbits are relatively round. Most of your numbers are close to 0. When you start comparing them to each other, you can figure out which one is more elliptical, which one is less elliptical, which one is more eccentric, which one is less eccentric. So out of our planets, the least elliptical with the lowest eccentricity is Venus, okay, which is the roundest orbit. Mercury has the most elliptical orbit. Okay, it's going to have the highest eccentricity at 0.206, which means it's going to have the most flattened orbit out of any planet in the solar system. So Kepler's third law, okay, states that when a planet is close to the sun, it's going to move faster. When it's farther away from the sun, it's going to move a little bit slower. And it all is caused by gravity. Okay, gravity is going to be based upon 2 factors. The size of the object and the distance between the 2 objects. So in this case, you see Earth and the sun. Okay, you can see on the left-hand side of the orbit, we're a little bit farther away. That's our summertime. Okay, as Earth travels around here, you'll see that that's where our weakest gravity is going to be. That's where our slowest velocity will be. As we travel 6 months later to our wintertime position, that's where our strongest gravity is going to be. That's where our highest velocity is going to be. Okay, velocity is just another word for speed. Okay, thanks a lot.